Hello my dear student, hope you are fine and taking care of yourself at your home. Today we will do the recapitulation of the chapter, as you know that we have completed the chapter. So before starting the recapitulation of the chapter, please do like and subscribe my channel and press the bell icon button for further notifications. So let's start the recapitulation of the chapter.
Further, you will observe that if you place the compass above the wire and allow current to pass from the south to the north, the compass needle deflects to the east. If you reverse the direction of the current in the wire, the direction of the deflection of the magnetic needle is reversed. The angle of deflection is directly proportional to the strength of the current through the wire. A magnetic field is the extent of space surrounding a magnet where the magnet's effect can be felt. Thus, it represents the region under the influence of the magnet, just as an electric field represents the region of electric influence. A magnetic field consists of a number of magnetic field lines, generally referred to as magnetic lines of force. Magnetic field lines represent the lines of action of the force acting on a unit north pole placed in the magnetic field. Are closed continuous curves. Never intersect each other. Mutually repel each other. Travel from the north to the south outside the magnet. And travel from the south to the north within the magnet. No magnetic field is spread around a straight current-carrying conductor. To begin the experiment, we fix a white sheet on a cardboard, which is clamped to a stand. Next, we pass a thick copper wire connected to a battery and key through a hole at the center of the cardboard. Finally, some iron filings are sprinkled on the board and current is allowed to pass through the wire by switching the key on. You will observe that when the current flows through the wire, the iron filings arrange themselves in a concentric circular pattern. By placing a magnetic compass on any circular field line represented by the iron filings, you can also detect the direction of the magnetic field lines. The direction of the compass needle indicates the direction of the magnetic field. Further, if you change the direction of the current in the wire, you will observe that the direction of the compass needle is reversed. Thus, based on this experiment, you can conclude that a magnetic field is a field of a current-carrying circular loop. Through another experiment, we begin by fixing a white sheet on a cardboard and clamping it on a stand. Next, we pass a thick copper wire through two holes on the cardboard so that it makes a curve and forms the shape of a loop. Then, we connect the ends of the loop to a battery and a key. Finally, we sprinkle some iron filings on the board and allow current to pass through the loop. When current passes through the loop, the iron filings arrange themselves in two sets of concentric circles on the cardboard. Further, if you place two compasses on each set of concentric circles, you will notice that the needles point in opposite directions. This shows that the magnetic field due to a current-carrying circular loop takes the form of two oppositely directed sets of concentric circles. Magnetic field lines around a current-carrying circular loop have the following properties. The lines are circular near the loop and tend to get elliptical away from it. They travel in the same direction within the area enclosed by the loop. They are parallel to each other near the center of the loop, indicating the uniformity of the magnetic field. insulated wire wound around a soft iron core. The iron core is magnetized when an electric current passes through the wire. In other words, an electromagnet is a solenoid with an iron core. Electromagnets are more useful than permanent bar magnet in the following ways. Electromagnets have a stronger magnetic field than permanent bar magnets. It is possible to reverse the polarity of electromagnets, but not in the case of permanent magnets. Electromagnets can be easily demagnetized by interrupting the current. However, it is difficult to demagnetize permanent magnets. Exerts a force on the magnetic objects under its influence. Therefore, a current-carrying conductor kept in a uniform magnetic field experiences a force that tends to drive it away from the field. The direction of the force on a current-carrying conductor in a magnetic field can be determined using Fleming's left-hand rule. To understand this rule, stretch the forefinger, middle finger, and the thumb of your left hand, holding them at right angles to each other. If the forefinger gives the direction of the external magnetic field and the middle finger points in the direction of the current in the conductor, then the thumb gives the direction of the force on the conductor. An electric motor converts electrical energy into mechanical energy using the magnetic effect of electricity. You find electric motors in household appliances such as fans, refrigerators, washing machines, pool pumps, and floor vacuum. To cross a magnetic field, the free electrons in the wire experience a force that makes them move through the wire, inducing an electromotive force EMF, and thus an electric current in the wire. This process of generating an EMF in a conductor by moving the conductor through an external magnetic field is known as electromagnetic induction. When a conductor is moved in a magnetic field or kept in a fluctuating magnetic field, the magnetic flux linked with the conductor changes. This change in magnetic flux induces an EMF across the conductor. The EMF generated in this way is called an induced EMF, and the resulting current is called an induced current. The phenomenon of electromagnetic induction was first studied by Michael Faraday. Michael Faraday hypothesized that current induced in a coil is due to a changing magnetic field. To test this hypothesis, he conducted an experiment. You can observe this experiment to verify Faraday's law. To conduct Faraday's experiment, we will begin by winding an insulated wire over a hollow paper cylinder to make a coil. Next, we connect a galvanometer to the coil. Finally, we insert a powerful bar magnet in the cylinder with the south pole entering the coil first. We observe that when the magnet is moved in, the galvanometer needle deflects towards the left. When the magnet is moved out of the coil, the galvanometer needle deflects towards the right. If the magnet is not moved inside or outside the coil, meaning the magnet is stationary, the needle immediately returns to zero. The deflection of the needle when the magnet is moved in or out indicates that a current has been induced in the coil. Thus, an EMF is induced in the coil due to the movement of the magnet. Faraday's experiment confirmed that a moving magnetic field is necessary for electromagnet induced when a conductor moves in a magnetic field, using Fleming's right-hand rule. This rule is also known as the generator rule. To use Fleming's right-hand rule, stretch the thumb, the index finger, and the middle finger of your right hand, so that they are at right angles to each other as shown. index finger points in the direction of the magnetic field, and the thumb indicates the direction of the motion of the conductor. Then, the middle finger indicates the direction of the induced current in the conductor.